Morning, everybody. Nice to see you. And I think we're going to have a very interesting talk today on MR scanning, following on last week's CT scanning talk. Now, we've got a very special fellow talking to us. Amongst my colleagues, Jan Lotz is probably the best known radiologist in the country. To give you just a brief summary, his achievements go on and on, but he's got 4 master's degrees, one in radiology, one in neuroanatomy, one in history, and the last one, which he got in 2020, was in applied bioethics. He cum laude most of those. He is the man who did the first MR scan in the Southern Hemisphere, not just in South Africa, and that was done at the South African Medical Research Council in Stellenbosch. And then he did the first MR scan in private practice in South Africa. He was professor of radiology at Stellenbosch University, and he was awarded his emeritus professorship in 2016. He's a very impressive fellow. Jan, over to you. Thank you for helping us.
Thank you very much, Paul. I think I will start straight away. If we can maybe switch the camera off. I think my sound is better without the camera. Good. Good morning, ladies and gentlemen. I'm not a magnet physicist, and I'm also not a mathematician. I'm a radiologist. So these concepts, one really needs to understand the mathematical language, but we don't. So we really are working on basic concepts to understand the concepts behind magnetic resonance. And what I'm doing here this morning is I'm just going to tell you a story. And what I want you to have at the end is to have those basic concepts to understand what magnetic resonance is all about. So let us start off by just contrasting magnetic resonance with other radiological investigations. Plain X-ray, let us just for a moment look at the plain X-ray. The electromagnetic spectrum is something we all know about. And we know that we live in a very small part of it, which is visible light. But beyond us, in this way and in that way, there's a huge amount happening. Now, if we go to X-rays, I just want to point out to you that the higher you go this way, the higher energy you're encountering. And you've got a wavelength somewhere at 10 to the power of minus 12 and a frequency of round about 10 to the power of 20. That's the type of energy we use to generate X-rays.
Jan, ekskuus, ons verloor jou klank bietjie. Jy moet meer op jou mikrofoon praat.
Good. Better that way?
Ja, dankie.
Okay. So you have got to understand that this is a high, very high energy electromagnetic wave. We're going to project it through the human body, and there's going to be an interaction. Some of these X-rays are going to be transmitted. Other of these X-rays are going to interact with certain substances in the body. And what they interact with is they in fact interact with the electrons. If there are few electrons, like in oxygen, about 8, most of the X-rays will travel through. And we will see air in the lungs as black. When there's a higher concentration of electrons, like we see here, they will start interacting with these electrons. And this interaction will change the electrons in a way that this atom may become ionized. And this ionized atom may be a factor in causing genetic changes and induce carcinogenic effects over the long run. But the main issue is we see the contrast because there's interaction. The calcium we can see because there's interaction with the calcium, while there is transmission as far as the oxygen and the other air components is concerned. Here I have for you iodine with 53 electrons, and you can see why we use iodine substances to inject, because we can beautifully see if the kidneys excrete the contrast, we can see the entire urinary tract, purely based on the interactions of X-rays with electrons. So X-rays, electronic interaction, difference between absorption and transmission. I believe Phil has covered the CT scan with you. I just thought I'd just show you. We started a CT scan in Tygerberg. It was the first one in Cape Town in 1978. And we had one detector, one source, and one detector rotating around the body. And that took us 15 minutes to produce an image like this. And you can beautifully see in this image the pixelated. And I hope, I trust that Phil has covered with you the concept of a matrix and these little pixels that we see, subunits that we're seeing here. And you can see these images were highly pixelated, and it took us 15 minutes. Today, we get sub-second scans because we have arrays of detectors, and you can cut through this in under a second, and in one breath hold, you can produce all these images to reconstruct this beautiful image of the abdomen. Now, you may not know, but one of the two persons that received the Nobel Prize for CT scanning is a guy called Alan Cormack. Alan Cormack is Ronnebosch Boys High. He worked at UCT. And in the 1950s at UCT, he was already working on this concept of CT in biological tissue. He later married an American lady and moved to the States, but he was awarded with Jeffrey Hounsfield. He was awarded the Nobel Prize for CT scanning. That's just ultrasound. Completely different kind of energy. It's a sound wave, and it depends on transmission through fluid and reflection when it hits a solid substance like a gallstone. This is the gallbladder. It travels through the fluid component in the gallbladder, and it causes enhancement behind it. And where it hits a solid substance like a gallstone, it reflects the sound and it causes a shadow. Look how beautifully you can diagnose the gallstone within the gallbladder. But here we've got sound transmitting with reflection. There we've got high energy transmitting or being absorbed. So that's basically the difference. Now, what is MRI? MRI is different, completely different. Doesn't fit into any of these categories. Let me introduce you to the proton. Now, where do we find the proton? If we're dealing with ultrasound, we're dealing with tissues. Tissues are made up of molecules. Molecules are made up of protons. molecules are made of atoms, and atoms have a nucleus, and inside the nucleus of the atom, we find a little structure called the proton. And I want to introduce you to the proton, because the proton magnetic resonance can also be proton imaging. We are in fact imaging the protons. And I'll show you why we image, but let me introduce you to the proton. So there's the atom, there's carbon with several protons. But if we come to hydrogen, hydrogen is the one atom that contains only one proton, circulating electron. We essentially forget about the electron, and we say the hydrogen proton is analogous, hydrogen atom is analogous to a proton. So if we talk hydrogen atom, proton, we mean the same thing. But listen to this. The proton is a positively charged elementary subatomic particle fundamental to all atomic nuclei. Its positive charge is equal in magnitude to that of electron, and it has a mass of 1.673 times 10 to the power of minus 27. Wow, that's small. That's small. Now, what I need to tell you about the proton is it has a magnetic axis, so it has a north and a south pole that rotates around its own axis, but it also has this movement which is called precession, which is the same movement we see in a spinning top towards the end of its gyration. It's got this precessional movement. Now, I just want to tell you that if you look at it, the Earth is also a spinning magnet. The Earth has also got a magnetic field, longitudinal magnetic field. It also spins around its own axis. And it also has this precessional frequency. And the best estimate of this frequency is that it happens once in 25,700 years. Now, what I'm always interested in is, are we looking at the same thing here? Is this maybe something on a much greater scale? And this movement and this movement being the same thing, if we could work out a ratio between the mass of this and the frequency of rotation and the mass of this stage, I don't know. I've tried to work this out, but I would very much like if there are people in the audience that could tell us. But it looks very similar. It looks very similar, and it makes one wonders. Anyhow, we need to now concentrate on what the rotational frequency of this proton is. This frequency of this proton, the precessional frequency of this proton is what we're going to deal with. And this is the Larmor equation. It's the only mathematical equation that I'm going to present to you, but it's an extremely important mathematical equation. It tells us that the precessional frequency of this proton, the number of times that it gyrates in a second, is given by the field strength of the magnet that it's put in, times a very specific feature of each substance in nature. And that very specific feature is the gyromagnetic ratio. And here we have it. We have that a proton has a gyromagnetic ratio of 42.58 megahertz per Tesla. So if you put this proton into a 1 Tesla magnet, it will spin, it will gyrate at 42 million cycles per second. Now, 42 million cycles per second is a lot. Now, that is the Larmor equation. The frequency is a constant, which is the gyromagnetic ratio of a substance times the strength of the magnetic field in which we place it. Now, this is a very interesting story because these two guys, Bloch and Purcell, they received the Nobel Prize for chemistry in 1952 because they found out that one can do chemical analysis by putting substances in a known magnetic field and to find out at what frequency these were gyrating. Now let us work, just for argument's sake, only with a 1 Tesla magnetic field. Now let us for a moment just find out what this Tesla means. This guy is Nikola Tesla. Nikola Tesla is described as a Serbian American. He immigrated to America. And Nikola Tesla was the guy that is his statue at overlooking the Niagara Falls. He's the man that lit up America with 3-phase electromagnetic power. Now the Serbians immediately claimed him. He's not Serbian, he's Croatian. In Zagreb, I went to the place where he grew up, and I know for sure he's a Croatian. But you know, the Serbians believe that the Balkan meaning the land of blood and honey, that everything in the Balkan belongs to the greater Serbia. So he's generally known to be Serbian, but he is really Croatian. But anyhow, Nikola Tesla, the field strength of the magnet was named after Tesla and 1 Tesla machines. So for that power, for that amount there, we can put it 1. So now, if we want to do chemical analysis, we can go here and say what substance gyrates at 16 million cycles per second in a 1 Tesla magnetic field. And you can find out it's lithium. I don't think this is what Bloch and Purcell got it for. I think Bloch and Purcell got the Nobel Prize for working out what the gyromagnetic ratio of each substance is. I believe that's what they worked out, because those numbers could not have come with Moses from the mountain. Somebody worked them out. And I think it was a much bigger feat. So if we now combined Tesla with Bloch and Purcell, the gyromagnetic ratio with the field strength, we get the precessional frequency of the proton. Now, at a 1 Tesla magnet, it's 42 million cycles per second. Today, we're all working with 1.5 Tesla magnets. We're not working with 1 Tesla magnet. So for the rest of this talk, I'm going to work with a 1.5 Tesla magnets, which means that in these magnets, these protons are precessing at 64 million cycles per second. Good. Now, ladies and gentlemen, as you're sitting all there, and I can hear maybe next time I should get across to Hermanus and join the crowd. But while you're sitting there, you have these protons all over in your body. Now, protons are the main constituent of water molecules and fat. And there's a huge number of them in water and fat. I'll show you now. So this human body is really composed of about 70% water and various amounts of fat. So when we look at the human body, we can almost call this human body a three-dimensional proton map. So if we want to do proton imaging, we really have the ideal substance to understand what's going on in the human body. But while you're sitting there in Hermanus, all your protons are randomly orientated. They all run randomly orientated. They all have a precessional frequency, and they have a vector along the lines of that projection, a precessional frequency. But they randomly orientated. Now, let us say you come to Cape Town and we put you in a magnet. This magnet has a field strength along the longitudinal axis of 1.5 Tesla. I want to show you the main magnet. I want to show you that there are gradient coils in this magnet. And I want to show you that there's a radio frequency coil in this magnet. And I'll explain all this to you. Let us just see what happens when we place the human body longitudinally in a magnet of 1.5 Tesla. You know what happens? All these little protons start aligning with the magnetic field. The great majority along with the magnetic field, some slightly against the magnetic field. I'm not going to talk about these now because then we're going into quantum physics. For the time being, if a guy wants to walk in his hands, if he has the chance to walk on his feet, let's ignore them for the time being. Let's concentrate on these guys that are orientated along the long axis. So here you're lying in the magnet, and now you yourself has got some kind of magnetic property in the sense that these protons are aligned along the longitudinal axis, and we have this magnetic vector going from south to north. And you've got to understand it's spinning. It's spinning. You can almost visualize it as a narrow blue cone that's spinning towards the head of this patient. Now, I don't know why I always think of a traffic inspector in the computer, in the MR scanner, because I always think that he may have a blue light on top of his head that goes swish, 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 swish at 64 million cycles per second. But that's the concept, you see. That's the concept. That is the vector that is there. It is a magnetic vector in the longitudinal axis, and it's processing at 64 million cycles per second. Now you will find that we cannot measure that because it's going out in that direction. For us to be able to measure it, it's got to be perpendicular to any sort of radio frequency coil. But let me quickly tell you where this 64 million cycles per second seems to be around in the electromagnetic spectrum. If we go down here, 10 to the 10 to 4, 10 to 6 there, around, where are we? We are more or less in the region of short to medium radio waves. Now, I think we all from the same vintage. You may recall that on a Sunday evening, we used to listen to LM radio hit parade, and you would hear these short waves come and go, come and go. Well, it's the same thing. If we have a reasonably wrong radio transistor, we could in fact pick up this communication from the protons. But for that, we need to flip them through 90 degrees so that they are perpendicular to the radio frequency coils, and then only then we will start picking up something coming from the protons at 64 million cycles per second. We introduce a flip, and I'll talk to you about this excitation in a moment. But at this point, I just want to pause and tell you that we're on the point of hearing something coming from the protons. And to me personally, it sounds like music. It's not music. It's an electromagnetic wave. It's somewhere here in the high shortwave, almost medium wave frequencies. But you know, it's a phenomenal concept because for the first time, we are hearing the protons. And you know where they are? They are in the nucleus of an atom. They are extremely far away. So now, that's wonderful. I just want to leave you with one other thing. It's almost like George Bush the day at the 9/11 site when they said, we can't hear you. And he said, yeah, I can hear you. So I'm saying to these protons, I can hear you, but soon you will hear me. And the reason being that if we introduce energy at exactly the same frequency, we can talk back to the protons. Now that is something. That is something. Now let us go on. We're going to excitation. Remember now, excitation means we want to introduce energy so that we can flip these protons. It's not only for the flip, the 90-degree flip. It's also for another purpose, but I'll show you another purpose just now. Now, let us see what happens now. Now, here we go. I just want to explain to you. We're going to flip them through 90 degrees. Now, if on a very dark night, we have a person shining a narrow, highly intense light beam with a torch straight up in the air, and over a period of time, that person drops or moves that torch so that from a perpendicular position, it comes to a position parallel to the ground. If that person is on this merry-go-round and we outside the merry-go-round, this is what we'll see. We'll see the light spiraling down like this. If we are on the merry-go-round, we will not see that. We will just see this light moving through 90 degrees because this is a frame of reference. And if you are in the frame of reference, you only see what happens in the frame of reference. I'm showing this to you because we want to deal with this component, which is the easiest component to deal with. So we're now going to introduce additional energy at the same frequency in order to move these electrons. We want them to come from the Z plane into the XY plane. For that, we need to introduce energy, so they will be in a higher state of energy in the XY plane. And they would want to return to a position of rest. Now, let me show you what happens when we introduce this RF pulse at the same frequency of 65 millicycles per second. 64 megahertz per second. We're going to introduce that frequency and let's see what happens. You see? And then it relaxes again until it's back to normal. So you flipped it. Let's just look at it here from a position there. You flipped it there, and then you were able to pick up the frequency, and then it disappeared as it moved back to a position of strength or a position of rest. Important to control the amount of energy that you push into it. Because if you push in energy at the same frequency, it has to be at the same frequency. Let's see what happened. This is the Verrazano Narrow Bridge. I believe it connects the boroughs of Staten and Brooklyn in New York. Just after it was built, there was a gust of wind, or a very windy day. And the wind was blowing at a certain frequency, the gusts of wind down the valley. Now let's see what happened to the bridge.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging fist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables of...
I'm going to leave it here. If you want to know what happened to the bridge, you can see it all on YouTube. In the interest of time, I'm going to stop these now, but I think you know what it means to introduce energy at the same frequency and create a situation where there's an excessive energy into the system, in the system. It's either going to break down, or if you stop, it's going to return to a position of rest. So there you have it, beautifully, 90-degree pulse. You've got the RF coil right 90 degrees to it, and therefore you register the pulse. Okay, so there we are. Now we go to relaxation. Remember, now we've introduced energy. It's in a higher energy state, and it wants to relax back to where it was. No system wants to have additional energy that it doesn't want. It wants to get rid of that additional energy. Now we see it by way of relaxation. Let's just go through it there. We had the energy in the Z plane. We introduced an RF pulse that moved it into the XY plane. And now it's going to start going back in that direction, and it's going to become vertical again, when it's in a state of rest. So a different way of looking at this is we can almost look at this as a regrowth of the magnitude of the vector along the B-axis over a period of time. And if you look at it, you can see it follows a curve as it regrows. Beautiful curve. Time factor, the regrowth. Now, we call this relaxation, we call T1 relaxation or spin lattice relaxation. Why spin lattice relaxation? Because you have a fat molecule that's composed of many carbons and hundreds of hydrogens and even a few oxygens. And you've got a water molecule that's composed of an oxygen and 2 hydrogens. Now you've got excess energy. You want to get rid of the energy. Can you see that energy, excess energy, will simply disappear in this molecule? Because each one of these little guys can handle a little bit of this energy, and it will just disappear completely. So what happens? it will quickly return to its normal position. You see that? That's fat. Why? Because the lattice, the structure of this molecule is made to handle this excess energy. It just disappears. So we have that curve representing the fat return. This is fat. Covered that 100 yards in no time. This is water. Do you think water with 1 oxygen and 2 hydrogens can do the same that these hundreds of guys did? No, they cannot. They are struggling. They are struggling. That there's even a guy, water is further behind, just don't see him in this picture. It's never a straight line, but it's just to show you that water lags behind. Water lags behind. Water can't get there back to normal. It needs much more time to return to equilibrium. Now, what have we done on this picture here? You know what? We have created contrast between fat and water based on the relaxation possibilities of these, and this is based purely on how they are able to handle excess energy, and this is a factor of the lattice, the substance of the molecule. Now that is at the heart of radiology, because we have, of magnetic resonance, we have created contrast between fat and water. And if we're now going to reconstruct an image, I'm running ahead of time, but I'm showing you the image because I want to show you. This is the orbit. This is the globe. This is the lens of the eye. You can see that the water in the posterior chamber of the globe is black. Why? Because it has difficulty in returning, and it was low energy at the time that we took the picture. Or it was a low return of energy. Fat, on the other hand, is right up at there. Look at the intraconal fat, the orbital fat. It's white. And what I'm showing you here is really at the heart of the whole MRI process. It is the spin lattice of a T1 relaxation that gives us this beautiful anatomical image of the orbit. Now it looks easy, but now I've got to show you how it's done. Now let's just for a moment go. We've got the 2 major relaxation processes. We've got the T1, which I've just shown you. Then we have the T2. So what happens in the XY plane is not only that the energy disappears along the longitudinal axis. These are 2 completely different components, 2 completely different processes. And this energy disappears differently from the T1 energy. And this energy is called the T2 energy, or the spin-spin relaxation. And what you've got to understand here is at the time of the RF pulse, it's like a huge symphony orchestra. This is the conductor. It says play together. And for an instant, they're all in tune. They're all playing at the same frequency. And then the one guy started interfering with the other one, and they start losing coherence. And as they lose coherence, they lose the initial longitudinal vector. Let me try and explain it to you in this way. Look at the fat molecule. fat molecule with all these hundreds or thousands of components. It's like a symphony orchestra packed in a very close hall. There's the conductor. He says, we're now going to play. So the baton falls and they start playing together. But then the conductor disappears. And these guys are so tightly packed that the second violinist puts his elbow in the cellist's ribs. And there's a lot of interaction here between them. And they seem to not be able to play coherently, and they lose their coherence very quickly. And this is what happens in a fat molecule. Look how they lose their coherence very rapidly because of the severe spin or frequency interaction between these people. So that's what happens in a fat molecule. Look at the water molecule. Water molecule consists of a cellist and two violinists. And they can keep on playing in full coherence, in full harmony for a long, long time. And the longer you wait, the more they play in coherence. And water goes very slowly and fat disappears very rapidly. And here you have a beautiful T2 or spin-spin relaxation. And you can see we've created contrast between water and fat. Now the water is going to be bright, the fat is going to be black. Look how well we see the optic nerve now inside a sheath, and the sheath is filled with water. There's the muscle, somewhere in between fat and water. Look at the CSF in front of the temporal lobe, water. Wonderful process of natural frequency decay in a natural substance playing out of a period of time, with water being able to retain coherence much longer than fat. And for that reason, we can create the T2 image. Now, ladies and gentlemen, here is just a little bit complication as far as the T2 image is concerned. When we work with I've got no interest in Phillips, it's just that the only magnet I could see in construction. When we look at these magnets that are made by humans, the homogeneity of this magnet is exponentially remote from the coherence that exists in the coherence that exists in a natural molecule. So if we want to try and measure the natural decay curve of any substance with a man-made magnet, we've got no chance. We cannot nearly create that kind of homogeneity in these magnets. So what we see, in fact, if we try and do a T2 in one of these magnets, is everything disappears virtually immediately. It's called the T2 star effect. And it disappears completely, virtually completely, because this magnet is so inhomogeneous that it cannot measure this beautiful natural resonance that's happening in these molecules. And why do we need the T2 image? We need the T2 image because, look here, the T1 image is not so sensitive. There's a little spot there. But we really need the T2 image, where we can see, in the case of multiple sclerosis, we can see multiple foci of abnormality that looks like water, right on T2. So we need the T2 scan to show subtle pathology, and without the T2, MR would not be a diagnostic imaging tool. So we had to some way create a way of being able to measure T2. So they're trying to refine these magnets and they couldn't. And someone scratched back in history and found that this guy, Erwin Hahn, he was a German, and after the war came to America, and he was working in magnetic resonance. And what he did was something very special. Let me show you what happens. In this magnet, if you set off those, you've got them setting off the hare and the tortoise, and they're going to play out. All these molecules are going to play out, and they're going to lose frequency. But because this because of the inerbigeity of this magnet, it's like a hare running away from the tortoise. So there's an immediate loss of coherence. But if you at some point say, turn around, like you flip an egg through 180 degrees, the hare is behind and the tortoise is in front. And if you now let them catch up, and when they cross the finishing line again, you could measure the strength, and what you're on the natural decay curve of those molecules, of that specific molecule. You can now chase them this way again and let them come around, and you'll have another peak. And that peak will be on the natural decay curve of this natural molecule. A beautiful solution, an excellent solution to define the natural decay curve of a substance that is resonating and losing coherence like that. So this man essentially saved for us the T2 relaxation, and his name is Erwin Hahn. And like Barak says, let's give him a bells. Now you've got it. You've got it. You really have it. If you understand it up to here, you've got it. The T1 is relaxation up on the vertical plane. The T2 is loss of coherence in the XY plane. And the loss of coherence will depend on whether you can flip the system around, let them catch up again, and then you are still on the natural decay curve. And those are the two processes by which we create T1 and T2 contrast and images. Now, if you're with me up to this point, you will understand that we now have a huge amount of information. We know that there's fat, which we can see on the T1, and we know that there's water that we can see on the T2. We've got to place them in certain geographical positions. If we cannot place them in geographical positions, we don't know where they come from. So we've got to do some kind of acquisition. And for that, we use the gradients. Let me show you what we do. There's the human body along the longitudinal axis in the magnet. First, we're going to introduce a slice selection gradient, then a phase encoding gradient, and then a frequency encoding gradient. And here we've got those gradient coils. Now, what do we do? What exactly do we do? We want to cut, when we use the slices selection gradient, we want to view one specific slice. We can't view the whole body at one time. So we switch on the gradients. The gradients boost the magnetic field strength in this direction, and it subtracts from the magnetic field strength in that direction. So these protons, because of the Larmor equation, will be not, if we use a 1.5 Tesla magnet, they will not be processing at 64 megahertz. They will be processing at fewer megahertz. Those will be processing at higher megahertz. There will be only one little slice, which is probably, say, a centimeter or 5 millimeters thick, where they are processing at exactly 64 megahertz. And this is because of a gradient that we introduced. Now you put a 64 megahertz stimulation in there. None of these will process. It's got to be exactly their frequency for them to be influenced. None of these will be influenced by a 64 megahertz frequency insertion. So what you have only the slice, exactly the same in the head. There's the gradient. They're processing faster at the top, slower at the bottom, and just at that slice where you want, they're processing at 64 megahertz per second. So if you introduce your stimulatory frequency, that's where you will have the effect. So what have we done? We have selected the slice. We've got the slice. We know where we want to go. Now we we put the slice on its back. I just want to orientate you. Let's say, for instance, we've got the slice somewhere from the head. Get it from anywhere. Could have picked it from there. Now the slice is on its back. And if we're looking at a human brain, I would tell you that the nose would be in front, the left ear would be at your right, and the left and the right ear would be at your left. Right ear at your left, and the left ear at your right. Why? Because we're looking at it from below up. Now, there was a huge fight because the neurosurgeons often operate on people that are sitting erect, and they want to operate from above down. The ENT surgeons want to operate from below up. Now, there's some operations which neurosurgeons and ENT surgeons have to do together. And this is the problem. You come to a point where what is left for the neurosurgeon is right for the ENT surgeon. And therefore we decided, because there are more surgeons in general than neurosurgeons, the consensus of the position or the final consensus is we look from below up. Now, we're almost there. Let me just quickly tell you how we put these pictures together. I believe Phil told you about a matrix. You put a matrix across. Now, if you put a matrix with few blocks, 3 blocks by 3 blocks, you're seeing something, but you're not seeing spatial resolution. You're not seeing fine detail. So you've got to make the blocks smaller. The smaller you make the blocks, the better you see. Now, remember, we in CT, you work with pixels. It's picture elements. Each little block is a picture element. In MRI, you've also got volume. It's got a thickness. So we're working in volume elements. Generally, we work with a matrix of 264 by 264 in MRI. 264 rows, 264 columns. You can push it up to 528. 528 this way, 528 that way. But you've got to understand that whatever you do, you're going to pay a price. And the price you pay is that scan will take you twice the time that a 128 scan will take you. Good. Now we've got the whole business in the matrix. And the man who sorted this lot out, what we're now going to do with the matrix on the next slide is a guy by the name of Paul Lauterbur. He received Nobel Prize for the next slide. Because what we need to know, we've got this information. Remember the T1 and T2 information, we've got it. But we've got it deposited in a very specific pigeonhole. We've got to know where it comes from. Now, the pigeonhole should have an address in a row and in a column. And if we know the address, we can deposit that information that comes from that area directly in the pigeonhole. Now look what Lauterbur did. He said, if we put violinists in 3 rows of 3 columns, and we introduce a gradient. Remember now, the reason for a gradient, I've got this little thing. I wonder, it's the sound story. Let me just try and get it. There we go. If we introduce a gradient, we say we're going to make the field strength higher on this side and lower on this side. Now this is across the head. So the right ear is here and the left ear is here. Now if we introduce the gradient, we know that according to the Larmor equation, these will start processing faster. There will be a faster frequency. So we can immediately tell whether this is coming from the right ear or from the left ear. And this is exactly what we've done here. We've taken the 264 columns in a row. We introduced a gradient, and on the right, it's spinning slower, and on the right left, it's spinning faster. Now, the frequency related to the field strength is so accurate that we can define exactly, not only from the ear, we can define exactly from where in the right ear this thing comes from, purely based on its frequency introduced by a frequency encoding gradient. So can you see that we've now sorted out all the columns? We will know immediately if we see the frequency in which column it belongs, because we know the field strength in that column. Frequency sorted, column sorted. So when we have information and it runs at a specific frequency, we know which column it's going to go. What about the rows? The frequency in or the rotation, the precision is like little stopwatches. They're all in phase. They're all running in phase. This one is at 12, it's all at 12, 6, all at 6. But now we introduce a phase encoding gradient, and that's a gradient that's switched on for a few milliseconds and then switched off. What does it do? It doesn't affect this one. It bumps that one slightly oblique, And what I used to tell the students at the time when the World Cup was played here in Cape Town, I said to them, here at this level, these guys are hit by Jonah Lomo. You remember Jonah Lomo? These guys are hit by Jonah Lomo. And those guys are hit by Jonah Lomo's big booty. He flattens them. Now, you know, this is now the beauty, because now we know if it's like this, after in phase, it belongs to the bottom row. If it's like that, after Jonah Lomo's big booty has been in action, it looks like that. And you know what? We've got the specific address because we know the column and we know the row. We know on T1, it reacted like this. It returned fast, so we can put it in there. It's fat. Almost final slide. If you can bear with me a little while longer. Just see. There we go. Before we get there, we've got to understand that we want to place information in blocks. And with that, we want to build up a picture. Now, that information we can only get after a 90-degree flip. And then we get this squiggle. This squiggle contains all the information I've told you about before. You can see all those things, the frequency encoding, the phase encoding, even the T1 effects, even the T2 effects are all inside a very composite graph or a tracing. But all the information is in there. And we store this information in K-space in the computer. So this is the way the computer sees life. I used to have Lady Gaga in this picture, but you know, things have changed. So I thought I'd rather put this, the Afghanistan lady, it was on the cover page of National Geographic. It's by way of this process, a mathematical process of Fourier transform, that we can unbundle, decomposite this composite wave and find all the information that I told you about now. The positional information plus the substantial information, the qualitative information. It's all in here. And here, we've got to really, again, give this guy, Jean-Baptiste Fourier, a bells for decompositing all this for us. And here you can see what we're doing. You can see the pixel, the voxels at the background, and you can see we're starting to build up the picture with this information. We know the column, we know the row, we know whether it's fat on T1, whether it's water on a T1, we know it's water and fat. And we're building the picture. So here we go. Final slide. From the information in K-space, we start building the picture, we start filling the pigeonholes, and there are the images. Phenomenal concept. If you think about it, in fact, not rocket science. Ladies and gentlemen, that's where the talk ends. I thought I'd just show you something for the future. Maybe we can talk about this in the future. Hemoglobin, red blood cells carrying oxygen. When it is attached to oxygen, it has no magnetic properties. When it loses its oxygen due to activity, it becomes magnetic and we can see it. So we can see where the functional things are happening in the brain, what this guy is thinking at this moment or what he's doing. That's the idea. This has to do with diffusion. You know that molecules diffuse, but in the white matter tracts, which are the long tentacles of the cells, the diffusion can only happen in the long axis of the tentacle. Therefore, we can sort out the white matter bundles. This is spectroscopy. I'm not going to go in this, but we can identify specific molecules because the way the rest of the molecule shields the protons, and we can identify what molecules. I'm showing you two choline, which is a membrane indicator, and NAA, which is a neuron indicator. And when there's a tumor, the choline, because of new membranes, go up and the NAA goes down. And when we do a composite picture, we can see there's the tumor. There is the activity. That's where the activity is. And we can define this. If we combine this with this, we can say to the neurosurgeons, listen, this guy is right-handed. He's now moving his right fingers. Look at the activity in his motor area. Don't go through there to get to that tumor. He's going to lose his speech and his movement. You've got to go around this area. So I stop there. That is all you need to know. This is maybe for future reference. The beauty of putting this all together, all based on the concepts that I showed you this morning. I hope this was some enlightenment. It remains just an unbelievable concept to think that we are really conversing with the protons deep inside the nucleus of a cell. Thank you very much.
Okay.
Yeah, I'm sorry, you heard nothing. I was just thanking you for simplifying difficult concepts in the physics of radiology. These are not easy concepts by any manner of means, and you've done a good job for us. I wonder if anybody has any questions. Could you come up and just we'll just get the people to come up and answer questions so it can get broadcast on Zoom. Yeah.
Yeah, thank you. Yes, intriguing talk. Just a very basic question. How are these cycles of millions per second measured, determined? How can you determine these with accuracy, these cycles of millions per second?
Well, you know, this, luckily I was not involved in that. It's like Ronald Reagan, when he quoted George Washington, he said, well, you know, I must admit I wasn't there when George Washington exactly said this. So I wasn't there, but I think this is exactly what Bloch and Purcell did for us. Bloch and Purcell managed to work out the gyromagnetic ratio of each natural substance on Earth. Once you've got the gyromagnetic ratio, you know at what frequency it will spin in a certain magnetic field. And I'm not aware of that physics, but that is exactly where the Bloch and Purcell contribution came, is to identify that these things spin at 100 or 64 million cycles per second.
Okay, thank you.
How they did it, I don't know.
Phil, Gert remotely. Can I ask you a question, Jan?
Yes.
If you were to increase the field strength significantly and put the body in there, then the precessional frequency will increase. You can even increase it to the extent that the body will emit light. Is that right?
Gert, I think you are very much on track. I think there won't be a body long before it starts emitting light. But what I can tell you is they're working with 3 Tesla magnets, and they're now starting to work with 7 Tesla magnets. Now the interesting, and obviously all you do now is you take the 42 mega cycles per second, and you multiply it by 7, and you'll see at what speed it now moves. But the interesting thing about the 7 Tesla magnets, they tell me it's an automatic tattoo remover. You put a patient into a 7 Tesla magnet, and his tattoo comes off, unfortunately with the skin. So if you want to remove the tattoo, you can get into a 7 Tesla magnet, but you're going to need extensive skin transplants. But the point that you're making is very true. The more energy you put into the system, the more you are running towards a situation where it can probably start emitting light and eventually just disintegrate.
Jan, I wonder if I can just ask if you could define 1 Tesla. So we have a 1 Tesla magnet. My understanding is that is 30,000 times the Earth's magnetic field strength. Am I wrong?
I believe it's in the order of about 30,000 times the strength of gravity.
Yeah. So a 7 Tesla magnet is a serious machine.
It's a serious machine. Let me tell you another problem about the magnet. I told you that hemoglobin that contains iron, when it's coupled with oxygen, the oxygen shields the iron from the magnet. So oxygenated hemoglobin is not magnetic. But when it's used up and it becomes deoxyhemoglobin, which flows back to the heart and the veins, the oxygen is gone. Now the magnet is holding the hemoglobin back because of the iron. So there's no return. There's no circulatory return. And there is the possibility of getting a cardiac arrest because your arterial blood is flowing, but your venous blood is held because of the magnetic effect of the venous blood.
Just remind me not to get into a 7 Tesla magnet.
Not if you have a tattoo.
Yeah. Any further question? Jan, thanks so much for helping us out and giving us a lovely talk. Thank you.